Okay. Hello, everybody. Welcome to the session on vectors and tensors. Can you hear me all right? Can you hear me? Okay, thank you. Okay, welcome again. So this is the session on vectors and tensors. I'm Marcus from CAST. I'll be your session chair, and we'll have 4 very interesting talks in this session. If you have questions to the presenters, please already start posting them during the talk in Discord or the YouTube chat. That will make it easier after the talk. So our first talk will be given by Lena Cybulski from the Fraunhofer Institute in Darmstadt. Lena will present her design study on reader front visualization for engineering design, and this is joint work with Hubert Mitterhofer, Thorsten May, and Jörn Kohlhammer. And the authors are from Fraunhofer, the Linz Center of Mechatronics, and from TU Darmstadt. So please, Lena, go ahead with your talk.
My name is Lena Cybulski, and I would like to share with you our experiences with a design study that we conducted in collaboration with a research company called LCM, which operates in the mechatronics domain. Personally, I have always liked problem-driven research and the close collaboration with domain experts, but never really wrapped that into a systematic design study. But when I met a mechatronics scientist at LCM 2 years ago, I felt like the use case that he described was a good opportunity. We found practical guidance in the 9-stage framework, which you probably know. It was proposed by Sedelmeier and colleagues back in 2012, and we considered it as a blueprint, which we then basically implemented from start to end. So there we are, the VIS researchers and the mechatronics scientist as domain expert. And the use case that he described in our initial meeting was about optimizing the design of highly customized electric motors. So for each customer order, they need to consider many design options. And at least cost and efficiency of a motor are usually in conflict. So a unique optimal solution does not exist. So what you usually do is you compute a set of Pareto optimal solutions where it is not possible to improve on one criterion without sacrificing at least one other criterion. And from there, it is the responsibility of the motor designer to search for a good compromise. Then we went on and we spent a few conversations on understanding the particular characteristics of motor design. Starting from a customer specification, simulation is used to try out thousands of slightly varied design options. So motor design is characterized by a large number of alternatives, even when focusing only on those that are Pareto optimal. Finding a suitable compromise is a highly exploratory process, where design options need to be evaluated with respect to multiple criteria. Motor designers also need to be able to justify their decisions in front of their customers and to communicate the trade-offs involved. To complete our picture, we also observed the domain expert on a real-world scenario. And we noticed that their use of visualization and interaction was remarkably advanced, because brushing works across scatter plots, and the brushes are even linked to histograms that depict the underlying design parameters. So we can assume the knowledge gap between us and the domain expert to be smaller than you would usually expect. We then started to translate our domain understanding into something that we, as visualization researchers, can design for. So the alternatives to be visualized are basically data points consisting of about a dozen design parameter values and up to 10 criteria values. The high-level task is to decide for the most preferred motor design. This is known as multi-attribute choice. The visual design should also take the expert's workflow into account, which we found to be most similar to what decision theory calls the elimination by aspect strategy. Based on our real-world observations, we modeled the decision-making process in more detail. For this purpose, we reviewed existing task taxonomies and mapped the relevant tasks to the domain-specific workflow that we observed before. And this resulted in a task hierarchy. Tasks are addressed in chronological order, but the process might of course involve going back and forth between the stages. We then came up with a total of 13 design requirements, which are pinned to the tasks from which they were derived. As a complement to the low-level requirements, we also defined 4 higher-level design rationals, where blue indicates the property we prefer. And the most relevant properties for our design were the first 2. Preferring simple over flexible relates to the user interaction and originates from the elimination by aspect strategy, where filtering is the prevalent form of user interaction. So we think that filtering should not demand more effort than absolutely necessary, and it is our ambition to reduce the interaction to the minimum of operations required. For the visual encoding, we prefer a lossless mapping of design options, because it enables mortar designers to visually retrieve any criterion value from any design option at any time. For the visual design, we originally wanted to build upon the scatter plots because they were familiar to the domain expert. However, the domain expert was missing a multi-criteria overview of all design options. So we turned towards parallel coordinates because they offer a compact and scalable representation of both design options and criteria. User interaction is a central aspect, and we address it by 2 complementing concepts. One is to eliminate undesired alternatives using composite brushes. The simple over flexible rational in particular manifests in our novel preference brushes. They stick to the desired ends of criteria axis because these are the values that you would want to keep for as long as possible. And this means reduced interaction complexity because only one end can actually be dragged for filtering. The other interaction concept is to select desired alternatives. So having identified a good compromise, the mortar designer can click the polyline to store it for later in-depth comparison. Such flagged polylines are permanently visible and can be seen as an intermediate search result. Accessing the unique identifier of the final choice then allows the mortar designer to join it with external data from other tools, for example simulation software. To validate our visualization design in the wild, we deployed the tool to mortar engineers and observed how they interacted with it in their own working environment. One participant pointed out that whenever only 2 criteria need to be balanced, scatter plots are his visualization of choice, because the bending of the Pareto front directly conveys how much losses in one criterion need to be traded for a certain gain in the other criterion. However, most optimization scenarios come with more than 2 criteria, and for those cases, the domain experts particularly appreciated that they could view all available design options while simultaneously observing all criteria. One of them also wished for an opportunity to investigate the 3D models of the underlying mortar designs, because the geometry of a motor might have implications on the manufacturing process or the installation at the customer's site. Finally, another participant stressed that he could imagine the visualization to be used not only for the decision itself, but also for presenting it to the customer, because they are the ones who are affected by the consequences in the first place. So it is very important to verify the decision together with them and to have them understand on what insights and trade-offs the decision is based. We also confirmed these impressions quantitatively in a usability study, but for details on that, we refer to the paper. So I just took you on a quick walkthrough of our design study journey that we went on for about 1.5 years. Now in this time, we have developed a visualization tool that helps our domain experts do their work better. However, with design studies, it can sometimes be a little difficult to reveal the value they actually offer to the visualization community. So I would now like to talk about how the results of this design study might be useful to other visualization researchers. So we have this task abstraction that resulted from studying the domain expert's workflow and needs related to making a multi-attribute choice. And this abstraction might be useful to others in that it generalizes to other decision-making scenarios and might guide the domain characterization and visualization design there too. In particular, it might serve as a reference abstraction for a decision-making process to which other visualization researchers can compare the workflows of their domain experts. Then we have the Pareto front visualization itself. It provides an effective means for the domain experts to make their choice. So this use case adds to the body of application areas where a rather standard visualization worked really well and blended seamlessly with the domain-specific workflow. Beyond mortar design, parallel coordinates might also demonstrate their advantages in other application areas. So this might encourage other VIS researchers to deliberately consider the practicability of parallel coordinates for a newly addressed use case. Finally, we will reflect on our lessons learned, by which we aim to relate our design study to the larger area of problem-driven visualization. So, for the problem domain, we learned that transparency is key. For motor designers, it might have a particularly high priority because their customers actually pay for their decisions, and they should only need to pay for something they can understand. We also realized that the domain experts quickly adopted the parallel coordinates for their real-world tasks. They particularly appreciated that they could immediately observe the effect of modifying the brushes on the availability of options. Regarding the collaboration with domain experts in general, we learned that despite their limited visualization background, they sometimes have a quite meaningful understanding of their visualization needs. And we would like to point this out explicitly because we experienced an unnecessary detour in the design stage that resulted from us not listening carefully enough to their opinion on visualization aspects. In general, the way we put the 9-stage framework into practice is just one of many, but we hope it will give an inspiration to other researchers interested in design studies. So I would like to conclude with the following take-home message. Our parallel coordinates design supports any engineering expert who needs to gain an overview of a significant number of options, where each of these options is associated with a certain number of criteria. And I think, in general, we should give significant attention to such well-known visualizations before making design choices for novelty's sake. There's a lot more insights in our paper, so if you got interested and relate to our work, I kindly encourage you to go for a reading. Conducting this design study has left me even more excited about problem-driven research, and I am happy that we will continue this collaboration and take on the challenge to support design choices also for systems, where multiple components are operated together. And with this, I'd like to thank you for your attention, and I am happy to answer any questions or any comments that you may have.
Thank you very much, Lena, for the very nice talk and the very nice work. If you have questions for Lena, please post them in the Discord channel or in the YouTube chat. Okay, so there's a question. Do you intend to test the usability of your visualization system empirically, that is, speed, decision-making nuances in the future, or will you be focusing on more interview-based methods?
Thanks for this question. We would like to also empirically test the usability. So until now, we have only tested it quantitatively with the system usability scale, but only with 8 participants. So this would be definitely something for the future. But as we are focusing on the design study aspects and on also the aspects of collaboration with domain experts, I think qualitative usability studies and we're really doing interviews is the best way to really get an idea of how the visualization tool can be really put into practice.
Thank you. If you have questions, please post them in the chats. So maybe I can ask about, can you tell us about your implementation and your tool, how you implemented everything and how you get the data from your collaborators into your tool and how that all works?
Sure. So this is a web-based tool. We have chosen TypeScript and React for the technologies, and we are getting the data from simulation software of our domain experts, which we then parse and upload to the web-based visualization. And well, yeah, we try to focus on a modular approach, but as we have focused on a one view approach for this one to keep it simple, yeah, that was our approach.
Okay, thank you. Are your collaborators already using this tool in their daily practice, or what is the current state?
We are currently in the process of deploying it at our collaborators' site, or really putting that into practice. So they are really convinced by the practicability for their daily work. So they are currently testing new features and really trying to integrate that in their workflow. For now, that works really good. So we are definitely interested in going further in this direction.
Mm-hmm. So you had some considerations about the wide applicability of your design study, which is very nice, so that other people can also build on this. Do you also want to make your tool available to other people?
We are currently thinking about having a basic approach published as open source, and then we can have like those features that are tailored to specific applications or specific domain experts that would not be in the open source version, but we are starting to think about that, but this is not final yet.
Okay. Mm-hmm. Thank you. Do we have other questions? If you have questions, please post them. Okay. So do you think it would make sense to couple your attribute visualization with 3D visualizations of the engine that they are designing, or is that
yes,
would that be possible and usable? Or?
Yeah, definitely. Actually, we are in the process of doing so currently. So that was, as was already mentioned in the video, that was one of the wishes of our domain experts, and this is really a good thing, because having really a 3D geometry in front of your eyes, and this really supports the mental model. So describing a geometry in terms of design parameters is abstract, but having really this geometry in front of you is another dimension of being able to judge also the geometry, which plays an important role, of course, for the further process, so the manufacturing process, but also the installation. So this is definitely the plan for the future. Yeah.
Yeah. Thank you. It's very nice. Do we have more questions? Okay. No. Doesn't look like it. Okay. So if there are no more questions, thank you very much again. It's really nice talk and really nice work. Thank you very much again.
Thank you.
And you're already getting. There's a. Yes. Okay. That's just a comment. There's a lot of virtual applause already for your talk, so we can give you another round of virtual applause. Thank you very much. Okay, so the next talk in the session will be given by Yungbang Wang from the Technical University of Munich about a globally conforming lattice structure for 2D stress tensor visualization. This is joint work with Jun Wu and Rüdiger Westermann, and the authors are from TU Munich and from Delft University of Technology. So please, Yungbang, we're looking forward to your talk.
Professor Westermann, who's also my peer. Hello everyone, my name is Junpeng, a PhD student from Technical University of Munich. It's a great honor to share our work here on behalf of my collaborators, Professor Wu from Delft University of Technology and Professor Westermann, who's also my PhD advisor. This work is entitled A Globally Conforming Lattice Structure for 2D Stress Tensor Visualization. The concept of principal stress is mostly used in stress tensor field visualization, which physically refers to the normal stresses into the directions where the shear stress components vanish and mathematically corresponds to the eigenpairs of the stress tensor. There is no doubt that stress field visualization can improve our understanding of the material response to external loading conditions. However, this kind of visualization is challenging due to several reasons. Taking the trajectory images as an example, which is the most common visualization of 2D tensor fields, the red and blue lines are the major and minor principal stress lines, which are traced from the so-called seeds. Even though this visualization can also provide a global view on the stress distribution, it has weakness if seeds are not selected carefully. As shown here, the resulting grid structure usually does not convey the local stress state, and such visualization can result in abnormal distribution of trajectory density, which would mislead the interpretation of stress concentration. In this work, we propose a globally conforming beam structure, which overcomes some of the aforementioned limitations. Firstly, we introduce the use of beams as a visual abstraction to create a stress-following grid structure in multiple dimensions, which encodes the ratio of principal stresses into a geometry of elements. Secondly, we introduce a constraint optimization to achieve the conformity of beams at intersections. Thirdly, we provide different color mappings for beam edges to distinguish stress types or the relative stress magnitudes. Furthermore, we also explore the preliminary extension to 3D situation. This image here shows a result of our approach, where the intensity varying red and blue lines are the major and minor principal stress lines including principal stress magnitudes. The ratios of each grid cell indicate the state of local principal stresses. Our approach starts by creating such an initial graph, in which the user interactively inputs a series of positions and traces the corresponding principal stress lines from them. Here we term the principal stress lines and their intersections as the skeleton trajectories and nodes. This animation shows how the interactive construction works. We create the grid cells around each node as the lattice seed elements, which maintain the aspect ratios of principal stresses at each node. In other words, the two dimensions of the element here are positively related to corresponding local principal stress respectively. There is a sketch showing how to construct the lattice seed element. 4 positions on the skeleton trajectories around each node are determined by considering the ratio of local principal stress and a global length bound. Then the lattice seed element is created automatically by the intersected 4 principal stress lines traced from these 4 positions. As step 2 shows, several principal stress lines are traced from the positions around each node to construct the lattice seed elements. Here we term these principal stress lines as support trajectories. Now problem is, the support trajectories do not match. Apparently, we cannot get a conforming lattice structure from it. To address the unmatched issue, we introduce a constraint optimization to scale the lattice seed elements so that the corresponding support trajectories match. We build this control equation to achieve the optimization. Well, the objective function f is designed to be a metric for the global conformity, and the constraint function g is used to ensure that the shapes of the optimized seed elements can still encode the principal stress ratios to some extent. What's noted is that we relax the objective function into an explicit function with respect to design variables, so the entire control equation is derivable. Thereby, it can be solved easily by some efficient gradient-based optimizers. This image gives an intuitive way to show how the optimization works. We can say the objective function converges significantly, and the constraint function is always within the predefined threshold during the optimization process. After the optimization, we have the matching support trajectories, Along each skeleton trajectory, we distribute a set of sampling points and trace some new principal stress line segments from these points to curve the support trajectories into some lattice elements, whose sides vary linearly in between two seed elements. Here we call the lattice group connecting the seed elements as the beams. In the final visualization, we remove the skeleton trajectories and color-code the lattice edges to show the stress type we want. To validate our method, here we consider three notable stress fields. First, which are all from the same 2D cantilever, but with different loading conditions. The first two test cases are used to demonstrate the capacity when a trisector or a wedge degenerate point exists. Via the third case, we show a scenario where a large number of nodes is input. By comparing the support trajectories before and after the optimization, we can see the proposed optimization works very well in these three cases. It's worth pointing out that there is a limitation in our method. It would fail when a set of support trajectories fall within different topological regions, which are divided by the topological skeletons. Just like this image shows, where the gray dotted lines are the topological skeletons along the minor principal direction. Here we recommend some tips to avoid this situation. Firstly, one can guide the node placement by the topological features. If the problem still exists, then to relocate the input node position or scale down size of lattice seed element, the topological skeletons can be got by performing topology analysis to a stress field. Furthermore, the 2D perforated plate and femur slice are taken as additional test cases. We can see from the mid column that the optimized support trajectories also match very well. Here we color-code the mis-stress along the lattice edges to capture the potential stress concentration. Here we also give a more intuitive way to show the convergence. We show the comparison of the lattice seed elements from case 2 and case 3 before and after optimization. We can see that these lattice elements keep a good similarity. We also adapt this approach for 3D case, given that the principal stress lines in 3D tensor field do not intersect in general. The proposed optimization is not available here. Thus, we waive optimization process and only make use of the proposed beam construction method. But as a solution to ensure the conformity, we let the new beams only generated from the existing lattice elements. Once the lattice seed element is created, the construction of 3D beam can be simply shown by these three images. Firstly, we create the next element by tracing new principal stress lines from the existing element corner points. Secondly, we fit the new generated element face to best match the real principal directions. Thirdly, repeating the first two steps until the generated beam element reaches to the boundary. The initial lattice seed element is expanded by moving the three principal direction vectors of the input position, and these direction vectors are scaled by their corresponding principal stress magnitudes. We use three test kits to demonstrate our method for 3D, and in order to reduce visual clutter, beam elements are rendered as opaque cubes, and the anisotropy of stress magnitudes is encoded into grayscales of the element faces. In the first case, we consider a 3D cantilever with loading conditions like this, which induce a symmetric stress field. The left image shows the beam structure generated from one single seed element, and this image gives a branch-like beam structure, which grows out from the left one. We can see the generated beam structure is matching and captures the symmetry of the stress field very well. With the same solid object, but we switch the loading condition into this, then the structure is under a silver torsion. We can also see that from the generated beam structures. Here we use the 3D filmer to further validate our method, since the complex load dictation and the geometrical outline, which always incur torsional stress field and the complex distribution of anisotropy. The generated beam structure captures all of these features. In this work, we propose a novel method to visualize 2D stress tensor fields via a conforming lattice structure, which encodes the following features at the same time. Also, we finish a modification on this approach to visualize 3D stress fields. In the future, we plan to explore the possibility of generating a space-fading stress-falling grid in 2D and 3D based on this approach. Thanks for your attention. This work is partially funded by the German Research Foundation under grant number WE2754/10-1 entitled Stress Visualization via Force-Induced Material Growth.
Okay. Thank you very much, Chipeng, for the very nice talk. This is really nice work. So there is a question in the chat. The first question is, can you use lattice information for generating heat maps? What kind of features can you highlight that you could not get from the original stress fields?
Okay, good question. First one, we have not considered visualizing the heat maps, but I think heat map is a vector field, right? I'm not sure because I didn't consider it.
The color-coded scalar field, I guess. Yeah.
Yes, but if we can get the streamlines from the vector field or the hyperstreamlines from the tensor field, we can generate such a great structure. And the second one, what kind of features can highlight that we couldn't get from the original stress lines? Yes, in the original stress lines, let's take the 2D stress field as an example. The major and minor principal stress lines, which are intersected to each other, but we can also get a lattice structure, but the lattice shapes cannot convey the ratio of the principal stress. I think many times we care about the principal stress ratios because they refer to the tension and compression of the structure.
Okay.
Yeah.
Thank you. There's another question. What could be possible applications of this technique?
What? I'd say the stress field visualization, especially for some structure with complex topology or outline. The user want to see how the force is transferred within the structure, and how the different force trajectories interact to each other. We can use this technique.
Okay. All right. Are there other questions from the audience? Can you tell us a bit more about the errors that are incurred? So you're doing this optimization, and then you would originally have basically a glyph or like the cell that shows the anisotropy of the tensor. But then the optimization changes this, and you have a parameter that allows you to control this error. Can you talk about this error? How big the error is?
There is no theoretical way, but in all of our cases, we set 0.3 as a threshold to restrict the change of the lattice seed element ratio. That's it.
So it looks to me it's very small, but do you think it would be useful to visualize also how much the error is, or is it so small that it doesn't make any sense? So it's basically too small, the error. Is it small enough?
I think
it looks very small, right? In your images that you showed, it moves just slightly. So I guess visually there's not much difference, and you could
Yeah, because I would say technically the reason of the error looks so small is because in my application I also permit the interpolation within the segment, because we know the perceptual stress lines is a curve which is composed of different a bunch of short segments. I use I also use the interpolation in each segment, so it's very small. I mean, it's kind of a continuous lines. It's not a line which is composed of some segments. I think that's the reason.
Yeah. Okay. So I think you as I understood it, you place all the seed elements manually, interactively.
Yeah. Yes.
Do you think you could do that automatically, or is it better to do it interactively?
Yeah. We thought about that, but as we mentioned in the video, sometimes you have the degenerate points and the topological skeletons by performing the topology analysis, because the perceptual stress lines are very sensitive when they near the topological feature, these topological features. I would say if we extend this method to automatically, the robustness it cannot ensure completely, I would say.
Yeah. So I think so in the paper and in the talk you visualized the topological skeleton a bit. Are you showing that to the user? Or so I mean, are you just visualizing it for the paper, or are you showing the user first the topological skeleton and that helps them to place the seed points?
In 2D, yes, we show the topological skeleton, because we integrated topology analysis to our implementation. Before the user choose the positions they want, they can get the topological guidance, so they can.
Yeah. So are there other questions from the audience? If you have questions, please post them. And then I think also in the paper title you have only 2D, but you did a lot in 3D anyway. So what would you say is the current state of your 3D visualization, and how much needs to be done further to do this completely in 3D?
Because this method in 2D is calculated built on the intersection of the perceptual stress lines, right? But in 3D we cannot get these intersections don't exist. That's a major obstacle to extend it. But as I said, we provide a limited solution. We only encourage the new lattice element grow from the existing element. So that's kind of a trade-off.
Yeah. Yeah, I guess it's very complicated in 3D because they don't intersect. Yeah.
And another problem is in 3D we usually need to handle the occlusion and clutter. If we have too many beam structures, it's not informative, I would say.
Yeah. Okay. We have time for more questions. If you have more questions from the audience. Okay. Doesn't look like it. Okay, so if you don't have more questions, then thank you very much again, Chongpeng. I think this is really great work. It's a really novel idea to encode the tensor visualization like this.
Thank you, Marcus. Thank you, everyone.
Thank you very much. And also I want to remind everybody, if you have more questions to the speakers, so to Chongpeng now or to Lena from before, and later you can do that in Discord and you can keep chatting with the authors about questions.
Yes, of course you can. Welcome.
Okay, great. Thank you very much.
Thank you.
So the next talk in the session will be given by Maria Jesus Lobo from École Nationale de l'Aviation Civile. She will talk about feature-driven combination of animated vector field visualizations. And this is joint work with Alexandru Telea and Christoph Hörter. And And the authors are from École Nationale de l'Aviation Civile and from Utrecht University. Please, Maria, we're looking forward to your talk.
Hello, I will be presenting our work on feature-driven combination of animated flow visualization techniques. This is a work I did jointly with Alexandre Telea and Christophe Herter. Animation is an intuitive way to depict flow data because it can show flow direction, orientation, and magnitude. Several approaches exist to do so, such as texture-based methods, animated streamlines using a cyclic map, or particles that move through the field. Flow visualization techniques can also be combined. For example, Schroeder and authors introduce a system to combine different flow visualizations through sketching. Ornes and authors combine two different vector fields by depicting them through different visualization techniques. We argue that to design a technique that combines optimally flow visualization techniques, we need to understand how they behave according to flow patterns. To achieve this, we conduct a user study that compares how three different animated techniques behave according to local flow patterns. We focus on animated techniques because there is evidence that they can be more efficient than static techniques for steady flow understanding. We focused on techniques that can encode flow direction, orientation, and speed, and that can be computed in real time. We settled on oriented line integral convolution, image-based flow visualization, and a particle system. Oriented line integral convolution is based on line integral convolution. It uses a sparse texture and a ramp-like kernel to produce droplets varying in intensity in the direction of the flow. Image-based flow visualization is based on the blend and deformation of noise textures along the flow direction. Particle systems advect particles over time in the flow field, resulting in an animated point cloud. To try to have a uniform density, we make the probability of seeding a particle in a location depend on the flow field speed at that location. We consider 6 different features: center, repelling focus, attracting node, repelling node, and saddle. Here we have the example rendering for each technique. To compare the techniques, we chose a critical point detection task. This task has been used in previous studies comparing flow visualization techniques and requires understanding the flow both locally and globally. We asked participants to find 3 instances of each critical point each time. Here we have an example of a task. The participant has to find 3 different attracting focus. To select them, he clicks on them. We use synthetic vector fields for our task. We wanted to be able to control the number and type of critical points in a field. Using only one vector field could introduce biases, so we generate several fields of similar complexity. To achieve this, we use a grid of 25 cells, and we use 5 generators for the features center, repelling focus, repelling node, and attracting node. In each vector field, we add 3 instances of each one of these features. And each one of these instances is added randomly to one of the cells. To spread the critical points across the field, we keep only one of these points per cell. And saddles will be generated implicitly. And to keep the complexity similar across fields, we only use fields that have 10 saddles. So here's an example where we have 15 feature points introduced using the generator and 10 saddles created implicitly. The user study will consider the 3 animated techniques mentioned before and 6 features. Considering the different techniques' characteristics, we draw 3 hypotheses. First, looking at the different techniques, we hypothesize that because oriented line integral convolution and particle system are less dense around repelling focus and repelling node than elsewhere, detecting these 2 kinds of points will be harder with these techniques than with image-based flow visualization. Second, because oriented line integral convolution and particle system present higher density around points that attract flow than elsewhere, they will be more efficient to detect those points than image-based flow visualization. Third, as saddle points both repel and attract flow, they should be easier to find using oriented line integral convolution, because this technique shows orientation and direction explicitly through the droplets. Particle system encode direction only via the points animation, so it will perform worse. image-based flow visualization encodes direction in the texture patterns, which present lower contrast than oriented line integral convolution droplets. So it should work better than particle system, but worse than oriented line integral convolution. Here we have the mean time and mean error count per technique, and the pairwise differences between the techniques. The error bars represent the confidence intervals. So looking at the pairwise differences, we see that there is no evidence of difference between the techniques. But if we look at the results per feature, we see that some techniques work better for some patterns than others. For example, oriented line integral convolution and particle system are better than image-based flow visualization for attracting node and attracting focus. Image-based flow visualization is better than oriented line integral convolution for repelling node and repelling focus. And oriented line integral convolution and image-based flow visualization are better than particle system for saddle detection, and the three of them are similar for center. Coming back to our hypothesis, both H1 and H2 are supported. However, image-based flow visualization is as efficient as oriented line integral convolution for detecting saddles, so the third hypothesis is only partially supported. The results of the user study suggest that some techniques work better for some features than others. We propose a technique that composes these techniques according to the flow patterns. Here's the global pipeline of the proposed technique. Having a 2D vector field, we first detect and classify the critical points using the eigenvalues of the Jacobian matrix. Then we assign to each kind of critical point a visualization, and compute a weight map based on inverse distance weights, as shown in this equation. The weights will depend on the distance to the critical points. To assign the techniques to the critical points, we assign two types of critical point to each of them to have a balanced result between the composed visualization. Then we look at each pattern individually. If the first study found evidence of a technique being more effective or efficient than the other two, we use that technique for that pattern. Otherwise, we choose the technique that produced the lowest error count. So this results in using particle system for center and attracting node, image-based flow visualization for repelling focus and repelling node, and oriented line integral convolution for saddle and attracting focus. Here we have the computed weight maps for each technique. The weight maps will be used to determine the translucency of each technique, resulting on the mixed visualization. This visualization can be complemented with a color map representing a scalar value. Here we represent the flow magnitude. To assess if the mixed technique is indeed more efficient than the other three, we conduct a second user study considering the four techniques, and we will use the same task and same approach to generate the vector fields. We hypothesize that mix will be more efficient than the three other techniques for the critical point detection task. Here we have the results. In this experiment, we also asked participants to report on the difficulty of the task. We see that there is evidence that mix is more efficient than the three other techniques and produces less errors than particle system and oriented line integral convolution. It is also perceived as less difficult than the other techniques. Here we have the results per feature. We see that for each feature, mix is at least as good as the better technique between the other three. To demonstrate the technique, we create a visualization using real data coming from a wind dataset, depicting the wind direction and magnitude. Here we have images showing the magnitude of the wind at different altitudes. Thanks to this technique, we can transition gradually between different altitudes, and this helps us understand different weather patterns. For example, we see that at low altitude there are a lot of local flow patterns, but at higher altitude the flow patterns are sparser, but the wind magnitude is stronger. Here we see wind evolution across time. Meteorologists need to find out where and when do specific patterns, such as critical points, appear or disappear. Our visualization technique can help here, because when critical points appear or disappear, this will change the type of visualization around those locations. Here, for example, we see an attracting node appearing. Our approach presents several limitations. For example, in the first user study, we only tested 3 techniques, 6 features, and 15 participants. Then, when we tested the combination, we only tested 1 possible combination for the techniques and features. So, as a future work, we plan to compare more visualization, data, and tasks. Also, we used a simple detection and weighting function, but other, more advanced functions could be used, and would also be compatible with the composition technique. Thank you for your attention, and I'm ready to take some questions.
Okay, thank you very much, Maria, for the very nice talk. I think it's a very nice idea to evaluate which visualization methods work best and in what region and then plan them accordingly. So if you have questions for Maria, please post them in the Discord channel or the YouTube chat. Maybe I'll start with one. So can you tell us a little bit more about the weighting function, how you do that? So you do inverse distance weighting, and what's the influence to the blending of the different methods, and how many critical points, how close do you have to have them together? What happens when there is like a large region, where there's no critical point? Which method do you use then?
So we use the inverse weighting distance function, so we detect all the critical points, and then we will weight the different visualizations according to these critical points. So, for example, if there is a wide region with no critical points, we will combine the visualizations of the closer critical points anyway.
Mm-hmm. Okay. So the influence of the closest critical point is then spread over the region. I mean, it looks very smooth and nice, that blending. Yeah.
Thank you.
Okay. Do you have questions? Can you tell us a bit more about why you chose these 3 techniques? What your rationale is to pick those 3? I mean, they seem to fit very well together. But why did you pick these 3?
Yes, we picked them because we wanted first to focus on animated flow visualization techniques, because there is evidence in another user study conducted before by Colin Ware that they can work better for this kind of tasks. So then, to choose which techniques specifically, we wanted to choose techniques that are computed in real time and that can show speed, direction, and orientation in the animation, so that we can also afterwards vary the speed, and that we would combine them with color. So that was the criteria. So according to that, we selected these 3. But then the work could be extended to use other techniques also.
Okay, very nice. So there's a question by Michael Böttinger. He says, the composition looked nice. As for the wind time slices visualization, can this possibly be misleading as you create the vector field as steady for the different time steps?
Yes, so we are, for the wind visualization, we are rendering each time step for a fixed amount of time. So it could be misleading in the sense that we are not representing the time steps one after the other, but at the same time we have discrete time steps. So we thought this could give a perception or illustrate how the winds evolve across time, even if we are using only the steady flows for each time step.
Yeah, okay. Do we have more questions from the audience? So I think now you explained it kind of, but can you talk a bit more about steady versus unsteady flow and how do you blend the different time steps then? So as I understand it, you basically do an animated visualization of one time step, and then if you have multiple different time steps, you kind of morph between them or blend between them. How do you switch? It looks kind of smooth, but it's a bit hard to see how the field changes over time.
Yes, so we are at each time rendering steady flow. So for the user study, we only used one slide, so it was steady flow. And as for the wind, what we do is we render one time step and then the other, but to make it smooth, we will interpolate between the composition masks. So the different compositions will be interpolated between time steps so that it looks smooth and it doesn't create a separate the 10 steps that could be disturbing to see.
Okay. So I think that the image-based flow visualization and the particle visualization, of course, also works for streamlines and path lines, just depending on which you integrate. The OLIC basically only works for streamlines. It's the principle. But then you animate, so it could be a little bit confusing, maybe which part of the animation is coming from like that vector field changing over time. So are you for the image-based flow visualization? Are you integrating path lines or streamlines, and then
streamlines?
Between the streamlines?
We are only working with streamlines, and we do not interpolate we don't create intermediate steps between different time steps either, so that we don't introduce like non-existing data. We are also always showing the time steps. So yeah, maybe it might be misleading, but we wanted to do it like this so we can show different time steps because the methodologies use them, and it could show the evolution of wind. But investigating how we could use it for not unsteady vector fields could be interesting also.
Yeah. Okay. Do we have more questions from the audience? So Michael is saying the particle-based methods imply trajectories rather than streamlines. Yeah, sure. But you could affect the particles along streamlines, right? By just choosing to do that. So I think.
Yes.
So I think you basically do streamlines, although you could do path lines, I guess.
Exactly.
Is that correct?
Yes.
Okay. All right. Do you think it would make sense to choose a fourth method or one of the three for areas far away from a critical point again? Like we say you have laminar flow, and then you choose a different method for areas where. So now you pick the closest critical point, right? So I guess for some regions you would get a different method just depending on what the nearby critical point is. Do you think it would make sense to have something for like an uninteresting region, a specific method, or it doesn't matter which one you choose?
Maybe it could be. I think what we are when we have the compositing method, we have like there are regions that are more salient, for example, with image-based flow visualization. So maybe we could investigate that further, like what technique attracts more the viewer's attention, and then see if there is one that is less attractive, that this could be used to regions that we do not want viewers to focus on.
Yeah. Okay. Okay. I don't see any more questions. I have more questions. If not, then yeah, it was very nice work. Thank you very much. Thank you for the presentation. Let's give you a round of virtual applause. Thank you very much, Maria. Okay. So the final talk in the session, the next talk will be given by Vito Engelke. Vito is from Linköping University, and his talk will be about autonomous particles for interactive flow visualization. And this is joint work with Kyla Wong, Bernhard Prime, and Ingrid Hotz. And the authors are from Linköping University, the University of Magdeburg, and the University of Koblenz-Landau. Please, Vito, we are looking forward to your talk.
Hello and welcome to my presentation about autonomous particles for interactive flow visualization. My name is Vito, and this presentation is based on a paper we published in 2019 in Computer Graphics Forum. Let me introduce the topic. Particle systems in general have been well studied over the last years. They provide a very direct approach for flow visualization. Particles are intuitive, they are flexible, simple, local, and of course parallel. The number of particles in their seeding positions are crucial for the effectiveness and efficiency of the visualization. This leads to a trade-off between dense seeding and the problem of missing features. As an example, we can observe the well-known common vortex street on the top right side here. For this visualization, the particles were seeded in a dense fashion on the left inflow plane of the dataset. So we can observe that the particles are basically occluding each other and also hiding a possible visualization of the vortex right after the obstacle. In contrast, the bottom picture shows far less particles, but these fewer particles highlight the vortex developing right after the cylinder in a far better way than the other picture above. With this, we can basically formulate a wish list to our ideal particle system. Our ideal particle system should automatically adapt its density to the underlying flow field, basically highlighting features of interest and reducing density in areas of laminar flow. This automatic adaptation of density should be based on a user-defined criterion, like an importance measure. Of course, our ideal system should come with a GPU-based implementation, and ideally it would also be part of a whole interactive framework where properties of the algorithm can be changed and adapted to the underlying flow during runtime and in real time. With this in mind, we can directly formulate the requirements for our autonomous particles. The first requirement would be the reduction of visual clutter. Visual clutter is a result of dense particle seeding, so this one should be reduced. The second requirement stands in contrast to the first one. Here we want to highlight flow features, so the behavior near features is highlighted by increasing of the sampling rate. As next requirement, our particle system should allow for direct input, so direct interaction with the system itself should be possible at runtime and of course in real time. The last requirement here would be high performance, so our new algorithm should not behave or perform significantly slower than a traditional approach. With these requirements in mind, we can now formulate the idea behind the approach of autonomous particles. The underlying concept is to loosen the constraint of particles being something static. Instead, a particle can undergo different events like burst, split, and death. With this, we also move away from a fixed particle count into the direction of having a total budget of particles. One of the requirements was to highlight features while preserving context information. We achieved this by splitting existing particles when close to features and therefore increase the density locally. This leads to the formulation of context and feature particles, where context particles are the ones existing from the beginning and have not split yet. Besides to its position, each particle stores additional information, like its energy and generation. The pictures on the right side illustrate our approach. In the top figure, only context particles are shown. These are following the flow. The image in the middle row shows the context and features particles together, whereas the rendering of the context particles is deactivated in the last picture on the bottom. Note here how the system highlights interesting regions in the flow field automatically. Let me walk you through the algorithm step by step. Initially, we consider 3 particles which follow their path within the flow field. The 3 possible events of the algorithms are birth, split, and death. Here, for example, the particle at the top is deleted as its energy falls below a certain threshold. At this stage, one of the particles is split into 4 children. The position of the offsprings is determined by the configurable offset into a random direction. This leads to an increase in density in the close surrounding of the parent particle. The parent particle itself is then deleted. The newly generated particles can split further or vanish as the system evolves. The particle's behavior is controlled by a small set of particle and system properties. In the group of particle properties, position, energy, and current generation are most important. The system controls the current and total budget. Note that the total budget is only limited by the available GPU memory and the system's performance. In addition, the system has configurable properties related to split and death events. Specifically, these are general and additional sensitivity against the selected split criterion, the maximal allowed particle generation, and the magnitude of the displacement. Lastly, the system defines the amount of energy lost during each computation step for each particle. On the right side, the influence of these properties can be observed. In the top picture, for example, the system is configured such that the particles are dying before reaching the domain boundary. In the middle row, the magnitude of displacement during splits is decreased, which leads to particles staying closer together and form line-like structures. Lastly, in the bottom picture, the energy loss was decreased, which leads to an increase in particle lifetime. I want to conclude my talk by demonstrating the particle system on 3 different datasets. First is the very well-known Kalman vortex treat. As importance measure for particle splits, the lambda-2 criterion was used. Furthermore, the laminar flow was subtracted and only a single time step is considered. The image on the top shows the particle system in a developed state, where color encodes velocity magnitude. The bottom 2 pictures are showing the same state. One is encoding the particle energy on the yellow to red color scale, and the other particle generation in blue tones. The following short video will demonstrate the influence of different parameter settings onto the particle system. In this video, the used split criterion is the proximity to the obstacle. In the first part, the magnitude of the child displacement is decreased. This results in a more line-like structures. Now the particle lifetime is increased. This is achieved by decreasing the amount of energy loss per frame and particle. Note that all parameters also include a small random fluctuation. For the second dataset, I have chosen the delta wing simulation. Here, particles are randomly seeded at the wing tip, and again the lambda-2 criterion serves as importance measure. Note how the autonomous particles highlight the 2 main vortices forming at the wing sides completely automatically and without further user interaction. Lastly, for the aneurysm case, a different importance criterion is used. Here, the curvature as part of the particle's history is facilitated. Note how the particles reveal the complex vortex core automatically. This concludes my talk. I'm happy to answer any questions in the following Q&A session.
Okay, thank you very much, Vito, for the very nice talks. Very nice work. If you have questions for Vito, please post them in the Discord channel or on the YouTube chat. Okay, I see 2 questions. So the first question is, Marco Agus says, nice work. Did you also think to incorporate transparency for smoothing, splitting, birth, and death?
Yeah, we were thinking about that. I mean, in general, the rendering parameters are not related are basically separate from the algorithm itself. But you have to think about what we see is like something between 1 million and 2 million particles. So if a couple of them split in one frame, you can't even see that that one particle basically splits and disappears. So there is no need for a smooth transition by using transparency.
Okay.
But in general, it's possible to integrate that. Yeah.
Okay, thank you. There's another question by Michael Böttinger. He says, very nice work. And the question is, what exactly is the energy of the particle? It only depends on the speed, right?
So the energy of the particle is basically, it's a little bit, you have to see it like this. So if a particle goes through an area of laminar flow, there is no, the importance measure is quite low. So it goes to this area of laminar flow, but you don't want to let it disappear right away. So it loses energy, and if it stays in an area which is basically boring for long enough, then it's deleted. So this is why we have this concept of this energy. which is then lost. And also the other way around, if the energy builds up to a certain threshold, then it's the particle basically is so excited that it then splits into its children.
Okay, thank you. Then there's a question by Anke Friederici. When only looking at a static picture, don't background particles in laminar flow become random noise?
Yeah, absolutely, yes. So a particle system basically lives from animation. So this is it's very hard to communicate how your particle system highlights flow features in a static picture. That's very true. I mean, we have seen, for example, in the delta wing case, we have seen that it very well highlights these big vortices on the outside. And that was actually one of the most interesting cases where I used it. So there was no interaction besides placing the source of the particle system at the tip. Right, so that was all I did. So all the rest was done fully automatic by the system itself. And here you have a communication of the flow feature in a static picture, but it's also a very kind of simple flow, right? So you have a lot of laminar areas, and then you have these big two vortices. If the flow gets more complex, then a static image can't transport the information that well anymore. That's true.
Okay. There's another question by Philip Sadlo. He says, nice work. Could consecutive split and death events lead to the impression of cross-flow motion? Can this happen with typical parameterization?
Not that much. So, I mean, I left out some details which are explained in the paper. So, if a particle splits, then the children which then appear are more sensitive, or no, they are actually less sensitive. So the criterion which led to the split of the parent has to be even more expressed to lead to a split of the children. So with this one, we basically prevent like an explosion kind of thing, where you have a lot of consecutive splits in the same area. And this also prevents this cross-flow problem.
Okay, thank you. There's another question. If birthing is low, can one birth immediately trigger a cascade of splits? I think I saw some blobs appear in some of the visualizations.
Yeah, I mean, this is very similar to my answer before. So this cascade of splits basically cannot happen if you choose the parameter accordingly. So this additional threshold for the children, this is a user-defined criterion. So you can allow that basically, and you also can prevent that. There's even one more parameter which basically tries to dampen this cascading effect, which is a maximum allowed particle generation. So you can say like, okay, this particle here is basically the third generation, so I don't allow it to split any further. Because there are other particles in the system which are still generation 1 or 2, so they are allowed to split, but generation 3, I put a barrier here, so it's not allowed.
Mm-hmm. Okay. There's another comment that Michael Böttinger says, the idea reminds me of pathline predicates, only that the filtering is done while the particles' pathlines are computed instead of filtering pre-computed pathlines. It would be great to have the module available, for example, in ParaView.
Yeah, I mean, it shares similarities with pathline predicates. That's very true.
Okay, do we have more audience questions? Can you tell us a bit more about the implementation? So how did you implement this, and what's the performance? How many particles can you do in real time, and so on?
So the implementation is done with the use of CUDA. So it's an interop between OpenGL and CUDA. So basically everything happens on the GPU, the rendering part as well as the computation. Quite interesting is that the frame time, like 70% of the frame time goes into graphics. So the rendering is actually more costly than the computation. Then we have a straightforward RK4 integration scheme for look up into the vector field. And it is so the system without the adaptive part is like performing such that you can easily do like 16 million. I think that's the limit. This is like on a 1080. So this is like the area where we're dealing with. And with the adaptation on, we are in the area of 2 to 4 million, but this is not a problem because like these 2 to 4 million are this desampling is much better, so you get a much better understanding of the flow with so much fewer particles. And so yeah, we can like compare 4 million in this case with the 16 million without adaptation.
Okay, thank you.
Detailed numbers are of course in the paper.
Yeah. So is the rendering the most costly operation because of the ambient occlusion? You have this really nice ambient occlusion, or is it that's the main why the rendering is slower?
Exactly, and this ambient occlusion is also, particles are like a small little element in space, right? So normal ambient occlusion is not capturing that it's so very well. So it is a quite aggressive and quite costly version of an ambient occlusion.
Okay. In the paper, you described this sorting step, especially to get rid of the holes when particles get deleted or split. That's the most costly step of the computation, maybe? Is that the...
It's true, yeah. So what I implemented there is it's a bitonic merge sort. So what I wanted to have is like running all the cores at all times. So making sure basically that the graphics card is like fully working for each and every frame, and also for the sorting. So so I use this bitonic merge sort as an in-place variant. So I operate on the memory itself, and of course, if you like go more into detail, I communicate with the global memory, so with the memory of the graphics card all the time, right? So there's no caching, and that is not the optimal way how to do things, right? So you should not have this global memory communication, but I can't prevent that. And what I did for the theme of splitting and deleting is basically I want to make sure that I have an like kind of at least optimal access to that memory. So I use power of 2 access or power of 2 sizes all the time to have this coalescing. I mean, this constraint does not exist currently anymore in Qt. It was loosened, but it's still faster to do this coalescing. So this is why basically this theme of 4 or 8 children appears.
Okay, yeah, thank you. So are you seeding particles, just as context particles in the background, or do you, could you detect some features and do you seed there? Or do you say that the vector wing you put manually the particle system at the wing tips? Or how do you do this?
Yeah, there are different options. So normally, or for most of the things, I used like a random seeding within a box. That's basically the simplest thing. And there is also the system supports a mode where you basically keep the amount of context particles constant. So let's say you start with 16,000 particles, and they can freely move around and split. But you keep these initial context particles, so generation 0 basically, you keep them constant, the amount of. So if they are going down in terms of the amount of them, then you insert a couple more, and you insert at random locations. So this is, basically they appear out of nowhere. But that ensures that you have a constant coverage of the domain with context particles. Yes.
Okay, thank you. There's a question by Helmut Dolasch. He says, very nice work. Is the paper available for download somewhere, as I could not find it linked in the program? So I think I can also answer that. It's in the Computer Graphics Forum, right? You can go to Computer Graphics Forum, and there you have the link to the paper.
Absolutely.
Oh yeah, Marco Torini posted the link. The Wiley online library. All right. Okay, so are there more questions by the audience? Philip Sadler has a comment. It also seems to share similarities with the work by Bauer and Peikert on vortex visualization using adjusting particle density. Okay. So if there are no more questions from the audience, let's thank Vito again. Very nice work. Very nice talk. Thank you very much. Let's give you a round of virtual applause. And also, that concludes the session. Let's thank again to all the speakers. I think it was a very nice and interesting session. Let's thank you all again. Thank you, everybody, and have a great rest of the day, and enjoy your lunch break. Thank you very much.